What is voltage really? If you're looking for some misleading gravitational or hydraulic analogy, or for oversimplified lies to children, you are in the wrong place. What I would try to give here is a definition of voltage that is based on the actual relevant Maxwell equations, at least for the quasi-static non-motional case that applies to a wide variety of circuits. It will be a bit different from the incomplete version that is only valid in the first half of a typical introductory physics or electric circuits course, where all students are exposed to is either electrostatics or resistive DC circuits. It will be nonetheless a definition of voltage shared by several college-level textbooks: Popovich, Ramon, Rimanduzer, Barroso, just to name a few. I will list them in the description of this video. In order to make this video as long and as boring as possible, this is how I will proceed. After giving a short definition of what work is, I will express the electric force as the product of the electric field times the charge it is acting upon, and then I will define voltage as work per unit charge done against E, the electric field. From there, after expressing the generic electric field E in terms of its irrotational and solenoidal components, I will arrive to an expression of voltage valid for quasi-static systems that will show it is in general more than the usual potential difference. This formally summarizes this entire absurdly long video. In short, the expression of voltage I will derive here assumes instantaneous potential and uses the Coulomb gauge. While this might not be the most general definition possible, to keep the video short in the following I will only consider stationary circuits where, in addition, retardation and radiation can be neglected. This more general definition of voltage is the bare minimum required to understand where KVL comes from, what are its limitations, and how to correctly probe a circuit that doesn't move and doesn't radiate, but that is not necessarily a lumped component circuit. So let's start with the definition of voltage that is quite general as well as concise, especially considering I am leaving out some parts. Voltage is the work per unit charge that is done against the electric field when its application point is moved from one point to another. Let's take this one step at a time, starting with the general definition of work. For brevity, in what follows, I will drop the superscript X that stands for done by an external force, that is, against the electric field. The elementary work del W done against the force F when we move its application point by an infinitesimal displacement dl is equal to minus the scalar product of the force with the elementary displacement. Del W equals minus F dot dl, which becomes minus F times cos theta times dl, where theta is the angle formed by the force with the displacement. How does this displacement of the application point take place? Let's consider a small field detector that is a point-like element that will feel the force associated with the field at that point without disturbing the original field. This could be a small mass in a gravitational field or a small charge in an electromagnetic field. Let's say it's a test charge and we move it from point P to a point P prime very close to P. Now we don't want to introduce any acceleration of the test charge, so the idea is to keep the charge at rest in, say, point P by applying an equal and opposite force Fx, and then move the resting charge at near zero velocity to a point P prime that is infinitesimally close to point P. If the displacement dl is really infinitesimal, we can consider the force not to change during the displacement, so that fx equals minus f along the whole path dl. This means that the elementary work we are considering is actually del w equal fx times dl, which is equal to minus f times dl. This is where the minus sign comes from. If we adopt this sign convention, the work is positive when the application point of f is moved to a position that increases the ability of the system to do work. That is, it increases the energy of the system, while work is negative when it is moved to a position that reduces the ability to extract work from the system. The energy of the system decreases. It is easier to see what this means with a gravitational example. Consider a mass in the Earth's gravitational field near the surface. The force on the test mass is constant and always directed downwards. We can balance it by applying an equal and opposite force directed upwards. If we raise this mass in equilibrium at distance dh, we will put it in a position that will allow us to extract extra work from the system. The energy of the system has increased by the quantity mgdh. On the other hand, if we lower the mass in equilibrium at distance dh, we deprive the system of the capability of doing useful work. The energy of the system has decreased by the amount mgdh. Work along a finite path can be computed as sum of works along path, where the force can be considered a constant in module and direction, and ultimately as an infinite sum of infinitesimal work contributes in what will be called a line integral. But before getting to this, and in order to make specific examples in the case of the electric voltage and make it stick, it is better to first explicit the expression of the force F. Now, which force? If we want to establish voltages and currents in a circuit, we need some form of stimulus and a mechanism to convert energy, chemical, gravitational, thermal, electromagnetic, into a form that can be used by the circuit's components. The driving force on the charges inside the generator can be chemical, just like in the case of a battery, gravitational, thermal, and so on, as many sources of so-called EMF are available. A typical circuit will contain one or more EMF sources that will supply energy to the system and components that will be named in accordance to their dominant trait. Capacitors store and retrieve energy from the electric field, inductors store and retrieve energy from the magnetic field, resistors dissipate energy, extracting it from the system. To temporarily avoid the complication of having to introduce the electrochemical potential and what follows, I will only contemplate pure electromagnetic electromotive forces. This means that we will be considering only generators of electromagnetic nature. This is by no means a limitation, since we usually account for the non-conservative phenomena that go on inside a generator or a battery by the effect they have on the electric field that appears between its terminals, without actually caring about the internal processes that maintain the charge distribution at the generator's electrodes. So again, what force? When it comes to electromagnetic interaction, the electric force on a charge Q is in general given by Q times C plus Q V cross B. When dealing with circuits, V is in general the composition of the drift velocity of the charge relative to the element of circuit that contains it, with the velocity of the element of circuit that contains the charge. Specifying the velocity of each elementary portion of circuit allows us to deal with circuits that change both position and shape with time. Since this video is already going to be way too long to include the concept of motional EMF, we will limit ourselves to the case where both circuit and the electromagnetic field sources are at rest in the observer inertial frame. From now on, we will only consider circuits whose components and connecting wires are not moving with respect to one another and the observer. While I'm at it, let me highlight that reality is always more complex than our simplest models. And even if I am considering here a slightly more complex situation than the electrostatic one, I'm still making several simplifying assumptions. For example, I'm assuming the circuit path does not change neither under the effect of external forces like in a generator, nor as a result of its interaction with the electromagnetic field, like in a motor or in a shrinking circuit under the effect of massive eddy currents. This means that I am assuming the circuit is rigid enough and all the currents are small enough that the forces of attraction and repulsion between wires won't be able to cause any perceptible deformation. For the same reasons, I'm also completely disregarding the phenomenon of magnetoresistance. Despite what it might appear at first, all these simplifications do not constitute a significant limitation of the scope of application of the concept of voltage I'm going to illustrate. If there is a generator with moving parts, its innards will not be contemplated, and we will look only at the fixed coils on the circuit side without questioning the motional origin of the variable magnetic flux that makes it work. As hinted before, if you assume whatever generator to be able to supply a driving field that is independent from what happens in the circuit, in circuit theory terms, an ideal generator that won't budge its supplied voltage no matter how much current the circuit draws. The conclusion to follow apply to basically all stationary circuits in quasi-static conditions, and as such to almost all lumpable and even some not lumpable electric circuits and electronic circuits that are neither transmission line nor antennas. And again, which force? It turns out that when the circuit is neither moving, tilting, or changing its shape, that is, V circuit equals 0 for every single circuit element, the magnetic component of the force on the charges drifting inside the circuit doesn't do any work, even if the charges move with non-zero drift velocity because a current is flowing. This means that with stationary circuits, we can compute voltage considering just the effect of the electric field alone. What follows, therefore, we will consider the force to be the electric force due to the electric field E in the frame of reference of both circuit and observer. F equals Q times E. The elementary work done against this force is del W equals minus Q times E dot dl. And the elementary work per unit charge, that is the elementary voltage along the displacement dl, will be del V equals del W over Q, or del V equals minus E dot dl. Why using the symbol delta instead of the differential D? Because in general, both work and voltage do not admit a potential function. Therefore, elementary work and elementary voltage are not necessarily exact differentials. Let's revisit the sign convention. We can now get a better feeling of what it means to choose voltage as work per unit charge done against the electric field. When we move the charge against the field, that is, when we separate opposite charges or when we push together same sign charges, we are increasing the potential energy of the system. On the other hand, when a charge is allowed to move because of the force due to the electric field, when opposite charges attract, or when same sign charges repel, the system will reduce its potential energy and will eventually reach an equilibrium position where the potential energy is a minimum. This picture of a battery shows the elementary work done against the field to move a positive charge towards the positive pole. And we see that the work is positive because we need to put in some work to do that. So the arrow that represents the voltage of the battery, a positive voltage, goes from the negative electrode to the positive electrode. But notice that this convention is not shared by the whole world. Let's see now how to compute voltage along finite paths. When I gave the definition of elementary work associated with an elementary displacement dl, the shape of the path did not enter the picture because basically an infinitesimal displacement doesn't have a shape. It is when we want to compute work done along a finite distance that we need to account for the path that joins the initial and final points. We can construct finite paths by chaining together infinitely many of these infinitesimal displacement, consider the force constant along each one of them, and then sum the elementary contributes in what will be a line integral. When the electric field is constant in magnitude and direction, voltage along a finite length path can be computed by simply multiplying the projected magnitude by the length of the path. There are two notable special cases if the field is always directed along the path. Cos theta is always plus or minus 1, and the voltage is given by the magnitude of the electric field, which is expressed in volt per meter, times the length of the path in meters. Of course, with due sign. If the field is always orthogonal to the path, cos theta is always 0 and the voltage is 0. When we consider a finite path in a non-uniform electric field, we can resort to a finite or infinite sum of smaller displacements where the field can be considered constant, and with a limit passage we end up with a line integral. A word in the notation, notice that I have to specify the path and the orientation by giving gamma, the path, and the order from the start A to the finish point B. Sometimes we abuse the notation and we call V gamma from A to B just VBA sub gamma. This is because when we reduce it to the conservative case, we want it to look like VBA equals VB minus VA. The ordering in the underscripts has to do with the integral extremes. For this reason, I will be using the following notation. V for gamma from A to B equals minus the line integral over gamma from A to B, and I will call it VBA gamma. As we will presently see, it's only when the electric field E is conservative that the integral depends on the extremal points alone, and we can drop the underscript gamma and represent voltage across 2 points by a generic arrow that goes from the start point A to the end point B of the path. This is what I implicitly did when drawing the arrow, representing the voltage across the battery. And this is what is customarily done in lumped circuits when drawing arrows that represent voltages, like in this figure. With the convention adopted, a positive value associated with the arrow means the positive work is done against the system when moving a positive test charge in the direction represented by the arrow. The tendency of the system, on the other hand, would be to do work to push positive charges in the direction opposite that of the arrow. The arrow of voltage is directed from the point of lower energy to the point of higher energy. Notice that many German-speaking countries use an opposite convention. The direction of the voltage arrow is reversed, but at the same time, the line integral that defines voltage is that of plus E dot dl. More on these later. As a visual aid when dealing with non-conservative circuits, we can generalize the notion of generic oriented arrow by turning the generic arrow across 2 points into the specific oriented path along which the line integral of minus E dot dl is computed. Good. Now that we have ascertained that voltage is minus the line integral of the electric field along a given path, if we are given the electric field configuration and the path in space, we should be able to compute the line integral that gives us the voltage along a particular oriented path with endpoints A and B. Note that we do not need to get into the intricacies of retardation because in a quasi-static context, fields are considered to be propagating instantaneously. We need to answer this question, though. In a given frame of reference fixed with the circuit, what is the electric field E that should be considered in computing voltage according to this definition? Or rather, how many electric fields can there be in one point? The answer is that E is the field defined as the force per unit charge experienced in a given point. That is the one and only total electric field E thought, not one of its mathematical components that only live in our minds, such as its projections on the axis of some electric coordinate systems, or just one of its conservative and solenoidal parts. Electrons do not go around with tiny notebooks to compute how much of the electric field to ascribe to this or that component. All that they can experience is the resulting electric field, so that is what they react to. Humans, on the other hand, can go around with tiny notebooks and play with the theoretical and mathematical components or whatever they see fit. For example, they can decompose in their mind the one and only electric field and electron fields into two very significant mathematical components. In fact, Helmholtz's theorem states that under very general boundary conditions, any vector field can uniquely be decomposed into an irrotational part that admits a scalar potential and a solenoidal part that admits a vector potential. Any electric field E then can be decomposed into the sum of a conservative electric field described by the scalar electric potential phi and a solenoidal electric field described by the vector magnetic potential A. As we will later see, in the quasi-static approximation, we use the Coulomb gauge, divergence of A equal to 0, that results in the electric potential obeying Poisson's equation, with the other condition that the displacement term in the Ampère-Maxwell's equation be negligible, even the vector potential will be a solution of a vector Poisson equation. These are potential type partial differential equations that do not contemplate any form of propagation, so the potentials have the same functional form they have in the static case and can be considered instantaneously updating, so to speak. The total electric field will be given by the following expression: E equals the sum of minus the gradient of phi plus minus the time derivative of A. I fixed the sign according to what will be explained in the next video. When we use this expression for E in the definition of voltage, we can decompose the line integral into the sum of the line integrals of the two components of the electric field. And we can observe that since the conservative part E irrotational admits a potential, the scalar electric potential phi, we can express this component of voltage as minus the gradient of phi and reduce that partial contribution to the difference in the values of the scalar potential. This line integral is path independent and its result only depends on the values of said potential at the start and end of path. Note the naming convention that places the end point before the starting point in the undescript. We say phi BA to mean phi of B minus phi of A. On the other hand, the line integral of the solenoidal part E solenoidal can be expressed in terms of the magnetic vector potential A and represents the contribution of the EMF along that particular path gamma going from point A to point B. in the specified direction. This contribute, unlike the scalar potential difference, does depend on the particular path. We have therefore shown how, in a general quasi-static system, voltage is composed of two parts: a scalar potential difference that only depends on the endpoints, and a path-dependent contribute due to the induced field that depends on the path. When we express each of these in terms of their respective potentials, we get the following definition of voltage. V over the path gamma going from A to B is equal to the potential difference plus the induced voltage contribution. Now, since this second part is in general path-dependent quantity, all in all, when there are variable magnetic fields in the space we want to measure voltage, voltage has to be treated as a path-dependent quantity, and that is the reason for the subscript gamma in its notation. The path is, in general, important. This figure, different paths, show the values of voltage that would be measured by a voltmeter when its probes are placed along that specific path. As we can see, there are some paths that give consistently the same value, while others result in a different reading. This will be explained in detail in a later video because this video is already way too long. Allow me just to summarize what we have found so far, which is this formula for voltage. The reason for using a different symbol phi to denote the scalar potential is to avoid confusion between the voltage V over gamma from B to A and the potential difference phi BA to which it reduces to in the special case of conservative electric field. As a matter of fact, voltage equal to potential difference is just a special case. It is only when the electric field is conservative, like in electrostatics, or in the absence of appreciable change in magnetic flux, that voltage reduces to the scalar potential difference alone. In fact, under this assumption, the relevant Maxwell equation is the simplified curl of E equals 0, which gives E equal to minus the gradient of phi. The minus sign here shows that the field E is directed against the direction in which the potential increases. In this case, voltage is given just by the difference in potential, as shown in this simple elementary integral. We can see the reason for the abuse in the naming convention shown before. In the case of the battery voltage, when the field is conservative, we can call V over gamma from A to B just VBA. We invert the order of the letters, putting the endpoint letter before the start point letter to mimic the order of the difference in the values at the extremes of the integral, like this. Notice how in these circuits, where the field is conservative, or where we intend to measure voltage in a region of space where the field is conservative, because we are not allowed to go inside the generator, voltage has the same value for all paths joining 2 points. The only difference would be the sign if we invert the polarity of the probes. But we need to keep in mind that despite this conservative condition being a very common situation, as we will see in another video, it applies to all circuits with lumped components. This situation remains a special case of the more general situation where voltage is path dependent. Okay, I seriously doubt that anybody has reached the end of this video without dying of boredom. But in the next video, I will show the IEC definition of voltage, which is the same that I'm using here, and where does that electric field decomposition come from.